Imagine you are sitting inside a Mars habitat.
Okay.
The year is 2026, and suddenly this massive environmental alarm starts blaring.
Now, what you want to hear?
No, definitely not. Pressure is building up in this external valve, right? So you urgently command the habitat's central AI to, quote, vent the pressure.
Right.
But because of a massive 20-minute communication delay with Earth and a sudden burst of cosmic radiation that scrambles part of your data packet, the AI misunderstands your English command.
It loses the context.
Exactly.
Yeah.
It tries to guess the context of your incomplete sentence, and it decides to vent your entire life support system instead.
Oh, wow.
Yeah, just like that. It's over. And the culprit wasn't a mechanical failure or a broken seal. The culprit was actually the English language.
It's a terrifying scenario.
It really is.
And honestly, it is exactly what aerospace engineers are wrestling with right now.
Yeah.
When you are dealing with autonomous systems millions of miles away, the slightest linguistic ambiguity isn't just, an inconvenience. It is a fatal error.
Which brings us to the absolutely wild reality we're exploring with you today. Because to fix the most dangerous problem facing futuristic AI, NASA isn't looking forward. They are looking 3,000 years into the past.
Yeah, it's incredible.
Our stack of sources for this deep dive includes excerpts from a really fascinating article. It's called The Sanskrit Code, Engineering Absolute Logic for Deep Space. And we also have this incredibly detailed schematic infographic we've been reviewing titled The Sanskrit Shield.
Both are fantastic sources.
Yeah, and our mission today is to figure out how an ancient human language is literally being weaponized as a rigid mathematical compiler to solve modern AI's most lethal problem.
It sounds like science fiction, but it's happening.
Okay, let's unpack this, because my brain is still having trouble connecting ancient history with interstellar travel. I mean, why are our modern languages failing us so spectacularly out there?
Well, to understand the failure, we really have to look at the fundamental mechanics of how we speak to each other every single day. Think about how much heavy lifting context does in our conversations. The fluid, emotional nuance of modern human languages. The sarcasm, the shifting definitions, the implicit meanings.
Right, like how we use slang or tone.
Exactly. That fluid nature is what makes poetry beautiful. But in the unforgiving void of the solar system, nuance is a massive liability. You don't want poetry. You need absolute mathematical perfection.
And the sources single out the impending crisis surrounding the 2026 Mars habitat missions, specifically pointing to those latency periods. You mentioned a 20-minute delay.
Right. The sheer physical distance between Earth and Mars dictates a speed of light constraint. A signal sent from mission control takes roughly 20 minutes just to reach a Mars habitat.
20 minutes?
Yes, and then another 20 minutes for a confirmation to come back. So the 40-minute round trip means real-time problem solving is physically impossible.
So no live video chats with Houston to fix a leak.
Exactly. If an anomaly occurs, the autonomous AI running the spacecraft, or the habitat, is completely on its own. It has to execute complex decision trees based solely on the last set of instructions it received.
Let's put that into perspective for a second for everyone listening. We've all started our phones, right? Watching those three little typing dots bubble up on a text message.
Oh, yeah. The anxiety dots.
Exactly. If a friend takes 2 minutes to reply, it feels agonizing. Imagine waiting 20 minutes for a text message while your spaceship's hull is breached.
Right. And that latency creates a breeding ground for what programmers call semantic drift.
Semantic drift.
Yeah. Natural languages, like English, are incredibly fluid. The meaning of a sentence can shift dramatically depending on word order, tone, or even just missing words.
Oh, I read a great example of this one. So if I say to you, the man saw the boy with the telescope.
Right.
Who actually has the telescope? I mean, am I using a telescope to see a boy in the distance, or am I looking at a boy who is physically holding a telescope?
That is a classic example of syntactic ambiguity. Now, apply that to natural language processing, or NLP, in an autonomous spacecraft.
That sounds dangerous.
It is. When a traditional AI receives a command in English, it has to parse a massive amount of implicit context to figure out, who is holding the telescope.
Right.
And under normal conditions here on Earth, large language models are actually pretty good at guessing. But space is not a normal condition. Deep space is filled with cosmic radiation that actively causes signal degradation.
Meaning pieces of the command literally get deleted or scrambled in transit, like dropping service on a highway.
Exactly. In aerospace computing, they call it bit flip.
A bit flip.
Yeah. A high-energy particle strikes a computer chip and physically flips a 0 to a 1, which corrupts the data packet. So if a signal packet carrying an English command is degraded during that 20-minute transit, the AI attempts to reconstruct the missing context from the vague fragments that survived.
And it guesses wrong.
Yes. This leads directly to what the sources call semantic hallucinations. The AI guesses wrong, it acts on the hallucination, and just like in your opening example, it vents the wrong system.
It's basically like autocorrect on a phone.
That's a good way to look at it.
Yeah, I mean, when my phone guesses the wrong word based on my typos, it's usually just a funny, embarrassing text message. But an autocorrect failure on a Mars descent module is a billion-dollar crater.
Exactly.
But I have to challenge the premise here for a second.
Okay, go ahead.
If the problem is just that English has too many vague words and overlapping meanings, why go back 3 millennia? I mean, why not just sit down and build a better, stricter English dictionary for the AI?
You mean like a coded version of English?
Yeah, we could just program a hyper-specific, rigid version of English where every single word only has one hyper-literal definition.
Well, what's fascinating here is that it seems like the logical next step, right? But the problem isn't actually the vocabulary. It is the underlying architecture of the language itself.
The architecture.
Yeah. English is structurally noisy. It relies heavily on word order, it is full of redundancies, and honestly, it is plagued by exceptions to its own grammatical rules.
Before E except after C, right.
Exactly, and even that rule has exceptions. You can create the most precise, hyperliteral dictionary imaginable, but if the syntax connecting those words still requires the AI to interpret intent or puzzle out structural dependencies, you still leave a backdoor open for a semantic hallucination.
Oh, I see. So the foundation itself is essentially rotten for the purposes of programming.
For deep space survival, yes.
Yeah.
The sources emphasize that deep space requires a frozen, rule-bound language structure. It needs a framework that functions identically to a computer compiler, not a conversational tool.
Wait, let me jump in for a second to clarify that for anyone listening who might not be a software engineer.
Sure, go for it.
A compiler is essentially a translator program, right? It takes the human-readable code that a programmer writes, like, say, C++ or Python, and translates it down into the exact raw machine language of ones and zeros that the computer's processor actually executes.
Spot on.
And the defining trait of a compiler is that there is absolutely zero room for interpretation. It's binary. It either compiles perfectly because the logic is sound, or it throws an error and completely refuses to run.
Yes, and our current human-to-AI interfaces are just too messy to act as compilers. NASA realized they couldn't just patch English. They needed a linguistic framework that strips away ambiguity entirely by design.
Okay, so if we can't patch English, who writes the new language? Do we have teams at like MIT or Silicon Valley locked in a room trying to invent a perfectly logical code from scratch?
Well, they don't have to. The linguistic framework that achieves that mathematical perfection already exists. It was formulated in ancient India.
Which brings us to the Sanskrit solution.
Yes.
According to the 2026 AI research detailed in our sources, aerospace engineers are utilizing Sanskrit's rigid grammar as a structural skeleton for the neural networks that will govern these missions. But hold on, I really need to push back here. When I think of Sanskrit, I think of history. I think of ancient spiritual texts, poetry, and chanted mantras. I've heard it spoken. How on earth can a language used for ancient spiritual hymns be, as the sources claim, quote, devoid of emotional nuance?
It is a really vital distinction to make. We aren't talking about conversational Sanskrit or its literary applications here.
Okay, then what are we talking about?
We're talking about the underlying grammatical engine of the language. Specifically, the rules formalized by the ancient scholar Panini around 500 BCE in a text called the Ashtadhyayi.
Panini, around 500 BCE.
Yes, and Panini didn't just write a grammar book. He wrote an algorithm.
An algorithm 3,000 years ago.
Truly. The Ashtadhyayi consists of nearly 4,000 incredibly strict rules that dictate exactly how words are formed from base roots and affixes.
4,000 rules.
4,000. And these rules operate with algebraic precision. They feature recursive loops, meta rules, and conditional logic. The researchers in your sources are utilizing a concept native to this grammatical structure called Shabdabodha.
Shabdabodha, yeah. The sources translate that as literal and verifiable verbal cognition.
Think of it as a mechanism for stripping away the emotional payload of a sentence. When a sentence is parsed, using Shabdabodha, it is broken down into a pure logical dependency tree.
So no more guessing who's holding the telescope.
Exactly. There's no guessing. The grammatical markers physically attach to the words in a way that dictates their exact relationship, independent of word order. The language literally forces the user to declare the precise logical function of every single concept.
Wait, so you are telling me an ancient human language processes information using the exact same logical architecture that a modern computer uses to validate code?
It is structurally identical. Sanskrit isn't just an old language. It is a generative algorithm. Because its rules are mathematically consistent and largely free of the chaotic exceptions found in English, it naturally functions as a compiler.
That is wild. And looking at the infographic from our sources, the one called the Sanskrit shield, this concept really comes to life visually.
Yeah, it's a great graphic.
On the left side of the graphic, it shows this chaotic, messy cloud of English command packets navigating through space. They are depicted as these jagged, tangled lines with question marks hovering over them.
A really great visual representation of the danger of semantic drift and context guessing.
Yeah, it really is. But then those messy lines hit this glowing barrier in the center labeled the Sanskrit solution.
And notice what happens to the geometry of those lines once they pass through the barrier.
Right. They instantly straighten out. The tangled web turns into these clear, uninterrupted parallel trajectories shooting straight toward a rocket module. It's a striking visual metaphor. It implies that the language literally forces the chaotic data to behave logically.
Well, it is more than a metaphor, actually. It represents the actual mathematical filtering process. The neural networks governing the spacecraft are mapped directly onto the rigid grammar of Panini.
Ooh,
So when an English command is translated into this system, the messy, contextual guesswork is filtered out. The ancient logic demands mathematical certainty, completely eliminating misinterpretation by design. Sanskrit just does not allow for a single sentence to mean two different things. It is absolute.
I mean, I see where you're going with the software theory. It makes total sense that a perfectly logical syntax prevents an AI from misinterpreting a command.
Right.
But, software is still just code running on physical hardware. And earlier, you brought up bit flips and cosmic radiation.
Yes, the physical threats.
How does an ancient grammar rule protect a mission from a physical cosmic ray blasting a hole in the ship's computer processor? Because we are moving from software theory into actual quantum hardware execution here, and the sources detail something completely mind-bending.
They do.
They are mapping the 4,000 rules of Paninian grammar directly to specific qubit states in quantum processors.
Yeah, and we need to build a bridge to understand how monumental that is. Let's start with standard computing.
Okay, the ones and zeros.
Right. A traditional computer bit can only exist in one of two states, 0 or 1, off or on. But a quantum bit, or qubit, can exist in a state of superposition,
Meaning it can be both.
meaning it represents complex probabilities of multiple states simultaneously. This allows quantum computers to process massive, complex calculations instantly. However, qubits are incredibly fragile.
Fragile how?
Well, in deep space, outside the protective magnetic bubble of our Earth, high-energy cosmic rays can easily knock these qubits out of alignment, destroying the data they hold.
And when a qubit loses its data in deep space, you can't just ask mission control to resend the file. That would take another 40 minutes.
Exactly. The spacecraft system has to heal itself immediately.
Okay, so this is where Panini's algorithmic grammar transitions from a software translation tool into physical hardware architecture.
You've got it. The aerospace engineers aren't just teaching the AI Sanskrit. They are structuring the physical dependencies of the quantum qubits based on the 4,000 algebraic rules of the Ashtadhyayi.
Okay, I think I have an analogy for this. Tell me if this works.
Let's hear it.
Here's where it gets really interesting. It sounds like a giant game of Sudoku.
Sudoku. Walk me through that.
Think about a Sudoku board. You have a grid of numbers, and the entire board is governed by rigid, intercepting mathematical rules.
Right, the numbers 1 through 9.
Exactly. Every row, column, and box must contain the numbers 1 through 9. Now imagine a cosmic ray is like a cup of coffee. Someone spills coffee on the board, leaving a massive stain that completely covers a specific square. The data is gone.
But the data isn't permanently lost.
Right, because the player doesn't have to guess what number is under the coffee stain. They don't have to hallucinate the context. They just look at the rigid rules governing the surviving numbers in that row and column.
The process of elimination.
Yeah, the surrounding mathematical scaffolding proves, without a doubt, that the missing number must be a 7, for instance. It physically can't be anything else.
That is a brilliant way to conceptualize it. The 4,000 Paninian rules act exactly like that Sudoku grid, but at a hardware level.
Wow.
If a cosmic ray knocks out a chunk of a transmission packet or it scrambles a set of qubits, the system doesn't guess. The grammatical rules map the dependencies between the surviving data points. The mathematical scaffolding forces the missing data to snap back into its only logical configuration.
So the grammar rules literally deduce the missing physical data.
Yes.
That is unbelievable. And according to the sources, this integration creates what they call the semantic shield.
The semantic shield. It sounds like a comic book superpower, but it is a highly advanced physical defense mechanism against cosmic interference, powered entirely by linguistics.
That's incredible.
Because when you are transmitting data beyond the heliosphere, signal degradation is a constant aggressive threat. Every single bit of information must be optimized for maximum clarity.
And I imagine it's incredibly efficient, too. Traditional human-to-AI interfaces, because of all that ambiguity we talked about earlier, must be incredibly redundant.
Oh, absolutely.
You had to send massive amounts of data just to make sure the AI understands the context of a simple command.
And that redundancy is a massive drain on bandwidth. By integrating these rule-based structures directly into the quantum deep learning models, NASA creates a hybrid AI that physically cannot misinterpret a command, and it does so using a fraction of the data load.
It's just so elegant.
It is a level of mission-critical survival insurance that simply cannot be achieved using modern natural languages.
It's blowing my mind that the survival of a multi-billion-dollar quantum AI system hurtling through the dark relies on the mathematical genius of an ancient scholar from 500 BCE.
It is quite the paradox.
But this brings up a huge question. If this perfect mathematical language solves our immediate communication crises for autonomous spacecraft in 2026, what happens when humans actually arrive?
Yes. The long-term plan.
The sources talk about the long-term future of non-biological communication, specifically predicting the rise of a universal space syntax.
We're looking ahead to the 2040s and beyond here. As humanity transitions from merely exploring the solar system to actually establishing habitats, the communication networks between humans, machines, and life support infrastructure must remain absolutely flawless.
So what does this all mean for us? The sources outline this grand vision of Sanskrit serving as the foundational code for the very first self-sustaining colonies on Titan, one of Saturn's moons.
Yes.
And this is where the daily reality for future astronauts gets really interesting. Are the colonists of the future going to have to sit down in a classroom and learn a 3,000-year-old language just to turn on the lights in their Titan habitat? Or is this all happening invisibly under the hood?
It is highly likely to be a combination of both.
Really? Both?
Yeah, the deep infrastructure systems, the life support, the automated agriculture bays, the atmospheric processing plants, they will all operate using this Sanskrit-based space syntax deep under the hood.
Okay, that makes sense.
The machines will communicate with one another in pure, absolute logic, completely invisible to the colonists. But for the humans actively operating and interacting with those critical systems, the dynamic changes.
Because they can't just yell an English command across the room and hope the automated systems guess the context correctly.
They cannot afford to. Therefore, the specialized engineers and colonists may actually need to adopt a spoken, highly formalized version of this syntax.
Wow.
They would need to structure their verbal commands with the exact same mathematical precision that the quantum system requires to execute the task safely.
Imagine what that actually looks and sounds like. You have a futuristic colony on a frozen moon of Saturn surrounded by rings of ice. And as you walk through the engineering bays, the spoken language echoing off the bulkheads shares the exact phonetic structure of the ancient temples of Earth.
If we connect this to the bigger picture, there is a profound poetic symmetry to that image.
There really is.
We are standing on the precipice of becoming an off-world species. We are building technology so advanced it borders on magic. Yet, our journey into the futuristic unknown of the outer planets relies entirely on the wisdom of our ancient ancestors.
It's beautiful, honestly.
We are taking the absolute best, most enduring intellectual achievements of human antiquity and merging them with the bleeding edge of quantum artificial intelligence.
It totally redefines what we consider advanced technology. Because for the last 40 years, computer science has been obsessed with teaching machines to sound like us.
Right?
We wanted them to speak our messy, emotional, modern languages so they felt more human. We built massive language models just to simulate conversational English. But in the end, to actually survive the stars, we had to abandon our modern tongues and teach the machines the most rigid, structured language humanity ever managed to create.
It serves as the ultimate bridge between humanity's deep past and our digital off-world future. We are utilizing our oldest algorithm to guarantee our survival in environments where biological communication was never meant to exist.
We have covered so much incredible ground today, and I want to make sure we tie all these mind-bending concepts together.
Please do.
Just to recap the journey of this deep dive for you, we started with the terrifying reality of the upcoming 2026 Mars missions. We looked at how a simple 20-minute communication delay, combined with the chaotic ambiguity of modern English, creates semantic drift.
The root of the problem.
Right. That drift causes deep space AI to suffer fatal semantic hallucinations, where guessing the wrong context leads to catastrophic failures. We then explored the brilliant pivot away from modern language entirely.
To Panini.
Yes, how aerospace engineers didn't invent a new code, but instead turned to Panini's ancient Ashtadhyayi. By using the concept of Shabdabodha to strip away emotional nuance, they turned the algorithmic grammar of Sanskrit into a natural compiler for neural networks.
A structural skeleton.
Exactly. From there, we dove into the quantum realm, looking at how mapping those 4,000 ancient rules onto fragile quantum qubits creates the semantic shield. And like a Sudoku board filling in its own missing pieces, this ancient mathematical scaffolding provides physical, hardware-level error correction against cosmic rays, ensuring no data is ever lost.
The flawless defense.
It really is. And finally, we looked ahead to the icy shores of Titan, envisioning a future where this 3,000-year-old perfect code becomes the universal space syntax for human colonies.
A fascinating future.
Definitely. Honestly, the next time you get frustrated by your smart speaker in your living room misunderstanding a simple request to play a song or set a timer, just remember the life or death necessity of absolute linguistic precision in the unforgiving vacuum of space.
The contrast between our terrestrial conveniences and interstellar survival is really stark. And while the necessity of this absolute precision for early colonization is undeniable, the sources prompt a lingering question that we should all reflect on. Well, we've established that to create this perfect semantic shield, we must utilize a framework entirely devoid of emotional nuance. We have to achieve pure, literal logic to prevent semantic hallucinations.
Right, you have to strip the emotion out.
But if the hybrid AI systems governing the entirety of our future Titan colonies are built on a foundational code fundamentally devoid of emotion, how will those off-world AIs eventually evolve to truly understand and perhaps empathize with the fundamentally emotional humans they are designed to protect?